Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. In this video we're going to be looking at the Arrhenius equation and using the equation in order to work out certain terms such as the rate constant K, temperature, etc. and using graphs in order to do this. Now it's quite clear from collision theory that as you increase the temperature of a reaction, the rate of reaction increases. And our explanation for that is that the particles have more kinetic energy, so on collision they have more likely chance of having that minimum amount of energy required for a successful collision. And this cause and effect has been explored in year 1 in collision theory. But we're now going to take this a bit more advanced and we're going to link this to the rate equation. So let's take our generic reaction with reactants A and B colliding together to form the products C and D. And imagine after doing some experiments on the effect of A on the overall rate of reaction and the effect of B that you generate the following rate equation. So it's second order with respect to B for the rate of reaction. Now importantly though, we want to tie in this fact here. Increasing temperature increases the rate. Well, if we look at the terms that are in this equation, we have concentration of B that will not be affected by the temperature. And then we have K. So it must be that temperature affects the rate constant. And this is exactly what the Arrhenius equation describes. The equation is saying as we increase the temperature, we're increasing the rate constant K, the value of this, and therefore, because that's linked to the rate, it increases the rate. And so we can think of this as a cause leading to an effect. Now, mathematically, this is described by this Arrhenius equation that looks like so. Rate constant K is the term A, which is also known as the pre-exponential factor. And this is just a constant. We don't need to worry about exactly what it means. It's just in the equation. And then we have the exponential, which is given this E, and the exponential of the activation energy, EA, over the gas constants times temperature. Now this is quite a busy equation. There's a few different terms in there, but for the exam you're going to be given this in the data sheet, so don't worry about that. What you do need to focus in is the units of each of these terms, and that is going to be really important. So firstly, let's just focus in on activation energy. Activation energy needs to be converted into joules per mole, so often it's given in kilojoules per mole, so that's really key. Temperature also needs to be given in Kelvin, so if you're given anything in degrees Celsius, you're going to have to plus that 273 in order to convert it into Kelvin. The gas constant is something that you're given in the data sheet. It's 8.31 joules per Kelvin per mole, and it's due to these units of the gas constant of why we had to change activation energy into joules per mole so that they match here and here. The exponential is a function that you'll find on your calculator. Now obviously different calculators vary, but if you have say a Casio make, what you're looking to do is find the natural log ln button, press shift and hit that button, because then that gives you this operation here, which is your exponential. When you're actually inputting the data in, the box that appears is where you would input this data here. And then finally, we have A, the pre-exponential factor. The units of this vary and they will match the units of the rate constant. Now we know the units of the rate constant varies depending on the overall order of reaction, and so they will be given in the question. That's not what the examiner is looking for. The examiner is looking that you can use this equation in order to generate some data and some ideas. Now previously, when we've ever done any experiments on rates of reaction, we've been trying to work out the order with respect to a reactant. In this case, what we're looking for is the relationship between temperature and K, the rate constant. So we're going to describe how we do this experimentally now in terms of the whole overview. So initially, like before, you're going to have to change the different reactant concentrations each individually, so keeping any other reactants constant as you change one of them. You're going to measure the initial rate, and then with this information, you can deduce the rate equation. And for example, if we have the rate equation K equals A times B squared, then from here, we can obviously rearrange this to work out what K is. And obviously, once we know what K is, we've got this part of our relationship. So what we need to do is then, having deduced the rate equation and rearranging it to get K, we need to then replicate this experiment, but this time keeping the reactants exactly the same and only changing temperature. So with these experiments, you then come up with a measurable rate, and from this rate, obviously using the rearranged version of the equation, we can then generate a value for the rate constant K. And obviously you keep repeating this at a variety of different temperatures, and so you will generate, once you summarize and consolidate all these results, a table that is the rate constant versus temperature. Now importantly, we can actually plot the data that's generated from this in a graph form. So we can do, on the y-axis, we can have rate constant K, whereas on the x-axis, we're going to have temperature. And remember, this has got to be in Kelvin because of our data here. Now, unfortunately, this form of the Arrhenius equation doesn't fit into a line graph. So what we need to do is be able to take this equation and fit it to a straight line graph. So you remember from GCSE maths or A-level maths, if that's a bit closer, that you can fit a straight line to the equation y equals mx plus c. So y is obviously any y value, so this is going to be related to our rate constant K. M is the gradient, and we're going to look how that fits into this part of the equation in a moment. X is our x values, which is going to link to temperature in Kelvin, and then c is our y-intercept. Now in this current form, this cannot fit this equation. What we need to do is remove the exponential here, this e. Now the opposite of exponential is the natural log ln. So what we're going to have to do is beat every term in this equation with the natural log ln. So our first one is going to be ln k, and that's going to be our y value. Then what we've got is a, and so that's going to have to be ln a. Now obviously the purpose of this was to remove the exponential because ln is the opposite, so we're going to have nothing there. And then what happens to all of this, which used to be to the exponential, is that then falls part of the equation. So fitting this to the straight line equation, ln a is c. The minus EA over R is our gradient, M. And then our temperature here is linked to exactly here is our X values. Now, annoyingly, this is the form that's given in the data sheet, but it's not quite user-friendly at the moment. So we're just going to separate out gradient and the X values. And so this part of the equation is exactly the same. What I'm going to do now is just remove the temperature to the side here to separate from the gradient. And what we're going to get is times 1 over temperature. And this will form our X values here. The reason it's 1 over temperature is because temperature is on the bottom of a fraction, and obviously you have to have a number on top. We've got the 1 there. So this is more user-friendly in terms of fitting it to this. And so, whilst this is given in the data sheet, this one is the one that you want to be really happy with using. Now, we're building up the picture here. This is an equation that will fit a line graph. So we could plot y versus the x. So imagine we've changed the temperature 3 times. We've generated the rate constant from this. We're going to plot this onto this graph. If we then create a straight line through those data points, we then have some information that we can obtain from the graph. So firstly, we can work out what ln A is. as where this straight line intersects the y-axis, this is our y-intercept, which links here to our C, our y-intercept, which is ln A. And then also, if we were to take the gradient of this straight line, then this gives us our minus EA over R, because this is our gradient M. So we're going to start to look at how we basically get to this point here and what we can do from there. Okay, so in a typical question, you'll be given the data and in temperature and the rate constant K. Now, the temperature can either be given in Kelvin or degrees Celsius. So obviously if you're given it in degrees Celsius, we need to get this into Kelvin. The next step is then to get this into a form that works in a line graph. And this is the equation that we're trying to fit it to. Now this is where you have to always remember that K is our y-axis, and that's going to be on our y-axis in our line graph, and then that temperature is our x-axis values, so that is going to be that. And just remember our c-intercept is ln A, and our gradient is minus EA over R. But importantly at this stage, we're just trying to get our data into this. So what you do is to take any value here in this column T and just do 1 divided by that value to get you your new values here. And then for ln K, you just take the natural log of the rate constant K. And just remember, on most calculators, like Casio calculators, you can see that the button's there with the exponential above it. What you then do is you plot the data, and it's plotting x values against y data, remembering that the x values and the y values aren't these ones here, but they're the newly converted values that we have in these two columns here. So you're going to have 1 over t here, and then you're going to have ln K on the y-axis. So if we had 3 lines of data, you'd almost do a scatter graph, you'd plot them, let's just randomly put them here. Then what you'd do is take a straight line with looking at these, so you'd find the best straight line that you can for the data. Now questions can vary, they can ask you to work out what A is, in which case if you haven't already, and it's good practice to always extend the straight line to intercept the y-axis, what you then do is you read the value here, and it's that value at the y-intercept that gives you ln A. But then in order to work out A, the opposite of ln A is to do the exponential. So in your calculator, you find that button there, shift ln, to make exponential. Then you put E, and then you put the value for ln A that you worked out from the graph there, and that will give you A. So if you were to read off, say, 31 here in the calculator, all you'd have to do is put E and then 31, and then that will give you 84.27 to 2 decimal places. Now alternatively, the question can actually ask you, or it could ask you in the same question, to work out basically the activation energy EA. So this is a really useful property. Because remember, the activation energy, if it's really high, it tells us that lots of energy is required to produce the products. So it's obviously going to have a slower rate. Whereas a lower activation energy is more likely to have a faster rate because the molecules don't need as much energy to have a successful collision. So it's a really useful piece of information that we can get from experiments. Now, EA is locked in the gradient M. So what we first need to do is work out what the gradient is from our graph. So again, with any gradients, make life easy for yourself. If you know it intercepts in the y-axis, then make your change in x start at this point on the axis and just choose a nice, easy to read area. So let's extend to here. So then looking at here, our change in x is going to be from here to the y-axis. And obviously, because this writing is in the way, I've just extended it here. And we're just going up here because that is the actual value of change in x. and our change in y is going to be from where in this line intercepts the straight line all the way to the top up here. Now with this gradient, we can then rearrange the equation m is minus EA over R. So if I keep EA fixed and move the gas constant over, then obviously R was divided here, so it's times the gradient, but that gives us minus EA. So we just need to get activation energy in a positive form. So we're just taking that negative over. So it's minus gradient, so whatever you work out as the slope, times the gas constant R, which is 8.31, and that's given on the datasheet, and then that will generate your activation energy. But remember, this activation energy, because it's linked to our Arrhenius equation, is going to be in joules per mole. This is really important because lots of questions on the answer line actually put it in kilojoules per mole. So you just have to do that next step of taking your answer and dividing by 1,000 to get it into kilojoules per mole. So this little diagram here shows you the flow of everything that you'd need to do in terms of an Arrhenius question. Part 6 obviously is taking us 2 different routes depending on what they're asking us. It would be worth ensuring that you know exactly what the process is here. So what I would do, okay, is pause the video here, blank the screen, and try and recall this all from memory. And then obviously put the screen back on and just check that you've got the right process, because this process is going to be key to these questions. Okay, so let's turn our attention to how this looks like in the exam. This is a 5-mark Arrhenius equation question. If you have graph paper, that would be really useful because you're going to have to be plotting some data in order to go further. If you haven't, just go through the motions and sketch out a graph and come up with a rough idea, but take that through just to show that you can do the calculations and you know what you're doing. So pause the video here and have a go at it, and then we'll walk through. Okay, so in this question, we're going straight from the beginning of our process. So we've been given temperature in Kelvin, so we don't have to convert that. And we've been given our rate constant for those different temperatures. And then these are going to be the data that you will have to plot in a graphical form in order to get some information from there that will allow you to work out the activation enthalpy. So they've been kind in this question. They've told you that 1 over T is what you need to do. And so you need to take the 298 and get this answer. And then we need to fill out this part of this column, which is ln K. So we're going to take the rate constant here and do the natural log of it. And you get this answer here. Now, what you need to do is exactly as it says here, plot a graph of ln K against 1 over T. Now, you'll notice it doesn't tell you which is the X and which is the Y. So the examiners want to see that you remember these. So ln K is always our y-axis and 1 over T is always our x, so it's definitely worth remembering this. Now we're going to then plot this data against each other, then we're going to draw a straight line and use that to come up with the gradient, and then rearrange with the gas constant to work out the activation enthalpy. So then we need to plot this data on this graph here. If we just notice the y-axis, it's negative numbers, so we're going to have to start at a -6 around here, going down to -14. And then the x-axis is 1 over T. It makes sense for us to start the lowest value here instead of 0, and then go 3.10, 3.20, etc. Now I'm going to list those in that form, and then in my units I'm going to do times 10 to the -3. And this is something to be aware of if you're doing the reverse. If you're given a graph and asked to read something off it, always check that you're looking at the units of temperature, because that can affect obviously the answer you get. So then we're just going to plot these points, and these are just being rough just so you can see. And then we find the best straight line fit for this data. That seems quite good. And then what we can do is work out exactly what activation energy is. So again, to work out the slope, I'm going to choose where it intercepts the y-axis because that's really easy to read off the x value. And then I'm going to choose a nice easy line to work off, so the 3.40 will be a good one. And then what I'm going to do is extend out my slope and then work out the change in y and the change in x from there. So it's here where it intercepts the 3.40, so we draw that across. So our slope is change in y over change in x, and if we read off, we've got 3.10 minus 3.40, and then our change in y is going to be from here to here where the grey line intercepts. So we know when we actually plotted this data that was at 3.10 exactly, so we know it's minus 6.57. Then we've got to do minus, and where the y intercepts here, going off this, is minus 10.6. And we just need to be really aware that obviously on here the units are to times 10 to the minus 3, as are up here in the actual on the actual x-axis. So including it down there is important. And then we just obviously work out the sum of here and the sum of here, and then actually work out the slope. And so we have minus 13,433. So this is obviously our value for m. We know that if we want to work out activation energy, we just need to rearrange this equation here. And so we've got EA equals minus m times r. The value of r we can get from the data sheet. So this is our gas constant here. M we've just worked out down here. Now it's a negative number here, but we have to, because of the way we've rearranged this equation, have a minus in front here. So the minus and the minus are going to make this a positive value for the activation energy. But if we annotate this all in, our calculation looks like so, and that will give you this value here. Now remember, this is in joules per mole, and often, as with this question, although it wasn't actually on the other sheet, was that this should be in kilojoules. So we just then need to divide this by 1,000 to get it into kilojoules, and then that will give us this as the value. Obviously, if they had asked about working out the frequency factor A, you would just focus in on this area here, the y-intercept giving us ln A, and then obviously to work out A, what we need to do is do the exponential of this value of ln A. So that looks like exponential of minus 6.6, which gives the answer of minus 3.88. Now the reason this isn't given as a question is because A should always be positive. Now for deeper reasons, this is a second order graph, so actually it will give you a minus k graph. But all you have to do is correct this to basically give you 3.88. So always look for A being positive, but they will actually design a question if they're going to ask you to get A, where doing this process here will give you the positive value for A. So this concludes the video on the Arrhenius equation. What we've done is we've looked at explaining how temperature affects rate constant and therefore affects the rate of reaction. And that is all given by the Arrhenius equation here. Rate constant equals frequency factor times the exponential of the activation energy divided by the gas constant times the temperature in Kelvin, and a negative there. And then finally, we've used this version that is also given in the data sheet, which is the y equals mx plus c version, which allows us to draw a graph and then work out activation energy and the frequency factor through the y-intercept. So some quite complicated stuff, but if you found this video really useful, please like it and then ensure that you subscribe to the YouTube channel for new videos as and when they're uploaded.